claro que los cuerpos cuadráticos son cuerpos cuadráticos reales, las curvas elípticas son cuerpos cuadráticos reales, son modulares. Y el problema de las iguales hay dos ocasiones de teorema de Marván. Luego también los impresionados trabajos sobre los estos de los cuerpos que la ecuación de verdad para ir dejando los elípticos. Correcto. Ellos lo van a contar.
Muchas gracias por la presentación. So today, in this talk, I'm going to try to explain to you what is called the modular method to solve, or at least try to solve, Diophantine equations. This is a method that was born with the work of Serre, Wiles, Mazur, and Frey, and its first success and its biggest success was the proof of Fermat-Last theorem. So our motivation for the talk is the following theorem, which you probably have seen before. Fermat-Last theorem says that the equation x to the n plus y to the n plus z to the n equals 0 when n is an integer at least 3. If we look into integer solutions, then all these solutions must satisfy that a times b times c. So a, b, and c are the numbers that go into x, y, and z, and a times b times c must be 0. And the second motivation is the following statement. All semi-stable elliptic curves over Q are modular. So the great magic about this modular method is that a statement about Diophantine equations is mysteriously related to a statement of modularity of elliptic curves. So in this talk, we have, let's say, 3 main objectives. And the first one is to make sense of this sentence. Our second objective will be how does this sentence relates to that one. And finally, we will see what kind of challenges arise when we try to study the same equation, but we replace the integers by a larger field. So this will require a lot of material, so I will spend some time introducing some ideas so that you can make sense of this modularity statement. You will see later, but let me just start by remarking already that this theorem of Andrew-Wiles was later extended to all elliptic curves over the rational numbers by the work of Breuil, Diamond, Conrad, and Taylor. So let's start by defining an elliptic curve. First, we consider a subfield K of the algebraic numbers that is a finite extension of Q. These fields, we call them number fields. And we define a Weierstrass model over a field K to be any equation of this form. Y squared equals xq plus a times x plus b, where a and b belong to the field K. This equation has the following discriminant that we compute from its coefficients. So now we assume that this number delta E is non-zero. In this case, we also consider the following set. So we consider the points with algebraic number as coordinates, x and y, that satisfy the equation above. And together to this set, we will add a point at infinity. So this is what we call an elliptic curve over K. Basically, an elliptic curve is an equation of this type with a discriminant which is non-zero. And then we consider its the points. So the first remarkable thing about elliptic curves is that we can define a group structure in its points. And the group law goes like this. So we take the point at infinity, for example, to be the identity of the group. And then we consider 3 points to sum up to 0 if they are in the same line. So we have the curve, we intersect it with a line, and the sum of these P, Q, and R must be 0. So this rule defines a group structure on the curve. And in particular, in this case here, so this is a tangent line. So we count the point P twice, and the third point is the point at infinity, which is the identity. So this means that P plus P equals 0. So this point here is a point of 2 torsion. There is another thing attached to an elliptic curve, which is going to be very important in the continuation. I will not define it. I will just give you the idea. And we call it the conductor. So this is a quantity which measures how complicated the curve is in some sense. And before we define it, I need to make just a few remarks. So we start with E over Q, an elliptic curve. And by some linear transformations of variables, we can assume that A and B are integers. And we can also choose such that the modulus of the discriminant is minimal. For such a model, then for every prime number L at least 3, we can reduce the equation which is on the integers modulo L. So this will give us another equation, E tilde, of this shape. And now our coefficients, A tilde, B tilde, they belong to the finite field with L elements. And this procedure, although here I say L at least 3, can actually be extended also for 2. We need to consider a little bit more general models to do that. But the point is that we can do this for every prime. So now, the conductor, as I said, it's a quantity, it's an integer that's going to measure the complexity of the curve E. And the second thing you need to know about it is that there is an algorithm that goes from this Weierstrass model that gives us this number. Okay? And this is called the Tate's algorithm. And finally, we can now define the first word on the modularity statement. A semi-stable elliptic curve is a curve where the conductor is square-free. So every prime that divides the conductor is going to appear in the conductor only to the first power. So P squared doesn't divide the conductor for any P. And now if we take a prime L, which is called a prime of good reduction, so these are the primes that do not divide the conductor, which are precisely the primes where this equation over the field FL also defines an elliptic curve. So those primes, they don't divide the conductor. And for those primes, we define the following number. We consider the number A sub LE to be L plus 1 minus the number of points defined over the finite field FL that satisfy this equation. So now this is an equation over a finite field, so we can just run through all possibilities, see how many times the equation is satisfied, and that's this number here. So this L is going to play a crucial role everywhere from the next slide until the end, basically. Okay, so next thing is we need to get a Galois, we want to get a Galois representation from the curve. I told you that these curves have a group structure, so it makes sense to consider the P torsion on this group. So this means we take all the points in the curve that satisfy the equation with over Q bar, such that P times the point is the infinity, which I said it's the identity of the group. One can show that this set of points forms the FP vector space of dimension 2. So FP is the finite field of P elements. And we can also show that the absolute Galois group acts on these points. So the absolute Galois group is the group of automorphisms of the Q bar that fix the base field Q. So this group will permute the points of P torsion. And from this action, we obtained a Galois representation. So if we take an elliptic curve over Q and P to be a prime, then putting this here together, we get a Galois representation. So this goes from the absolute Galois group into GL2 of FP because this is a dimension 2 vector space. And this is called the mod P Galois representation attached to E. But this Galois representation can be seen to have the following properties. So for every prime L of good reduction, so those that do not divide the conductor, there is an element which we call the Frobenius element at L, such that when we compute its image and we take the trace of the matrix we obtain, we get the number which is congruent modulo P to this AL. So these AL are actually traces of this representation attached to the elliptic curve. And the determinant at the same element is L, modulo P. And we have lots of Frobenius elements, so we have elements for every prime L, and these elements are dense in the absolute Galois group, and this somehow determines this representation, these conditions also. So these AL are very, very important. Okay, so first theorem, big theorem that goes into the proof of Fermat's last theorem is due to Barry Mazur, and it relates now all the ideas that I've showed you into one theorem. We take a prime P to be at least 5. We take E to be an elliptic curve over the rationals. We suppose that E is semi-stable, so its conductor is square-free. We assume also that the two torsion points of the curve are defined over Q, so all the two torsion points have rational coordinates. And this implies that the Galois representation that we have seen in the previous slide is irreducible. And here, by irreducible, I mean that we cannot conjugate its image into a subgroup of the upper triangular matrices. So the image is too large, is big enough such that it doesn't fit in here. So this is a very important theorem. Okay, so this finishes the crash course in elliptic curves. Now we go to a crash course in modular forms. A modular form is going to be an holomorphic function defined on the Poincaré upper half plane, and it will satisfy lots of symmetries. So we take matrices A, B, C, D in SL2Z, so the determinant 1, such that N divides C. So now this N is called the level of a modular form. So here I say weight 2 because we can define modular forms for several weights, but in this talk we just work with weight 2 modular forms. So a modular form of weight 2 and level N is an holomorphic function on the upper half plane, satisfying all these symmetries, where the level of the modular form divides this entry here. But inside the set of modular forms, we will consider only some of them, and we are interested in those which are cusp forms. And cusp forms have the special property that they admit a Fourier expansion of this form starting at n equals 1. In general, a modular form will also have another term for n equals 0, but a cusp form will start at 1. And these coefficients, a n of f, are in the complex numbers. The space of modular cusp forms is a finite dimensional complex vector space, and we have a family of commuting Eck operators. So these are linear operators that act on this space, and they commute. We call them Eck operators, and we index them by n. So because they commute, we can consider a common eigenvector. So let's say that f is a cusp form which is an eigenvector of all these operators. In this case, if we take the rational numbers and we add to it all its Fourier coefficients of f, one can show that the field that we obtain is actually a number field. So these numbers, which a priori are complex numbers, they are actually algebraic numbers. And they all together will give us a field which is a finite extension of the rationals. To such form, we call an eigenform. Okay, so we have now enough definitions to state the modularity theorem. So if we start with an elliptic curve over the rationals, then there is an eigenform f of E. This E is just to mean that this f is attached to the E, of weight 2, level NE. So the level of this eigenform is going to be equal to the conductor of the curve. And the field obtained by the coefficients is going to be the rational field. And the Fourier expansion of that form, we know that it has a Fourier expansion, will satisfy that for every prime L not dividing the level, the coefficient AL here is actually going to be equal to this AL of E that we have defined just by counting points on the curve. So we go from an holomorphic function into the elliptic curve by this relation. This is what we understand by modularity of an elliptic curve, but there is another type of modularity that is also very helpful for us in the continuation. We call this residual modularity, and it is a little bit less restrictive. And it goes like this. So if we start with an elliptic curve over the rationals, we have this mod P Galois representation attached to it. And we will say that this mod P Galois representation is modular of level n if there is an eigenform f of level n such that for all prime not dividing the level, so the conductor of the curve, we have that this AL of E is congruent to the Fourier coefficient of f at L, modulo some prime ideal, which is a prime ideal that is dividing P on the field of coefficients of f. Okay, so this is just a congruence. In the previous modularity type, we have an equality. So here we are only demanding to have a congruence modulo P. And we will, when this happens, we will denote this by rho bar, so tilde rho f of P. So for us in this talk, this notation is going to mean that we have a congruence like this. But you can see that this notation also indicates that we have an isomorphism of two Galois representations. But I won't talk about these Galois representations anymore, except for this idea of having a congruence between these numbers. So for the rest of the talk, this notation is not about an isomorphism of two Galois representations necessarily. It is on the back of it, but I'm just referring to this here. So corollary of the modularity theorem, well, we start an elliptic curve over the rationals, then its mod P Galois representation must be modular of level equal to NE. This is a corollary, very simple, because we have an equality, so we also have a congruence mod P. But here's one more idea that we'll need. So this, as I said, this congruence is less restrictive than the modularity of the elliptic curve E. So we know from this corollary that we have modularity of the mod P Galois representation if we just use the form that gives us modularity of the curve. But one can ask, can we find a different form that will still give us the congruence? And when we find such form G, whose level will divide the conductor and still gives us the same congruence, then we say that we lower the level modulo P, because we go from level NE into a level which is a strict divisor of NE. So we obtain a congruence, a new congruence, by level lowering modulo P. Okay, so we have now all the tools. We can go back to the first slide. So we now have more or less viewed what this statement means, and now we want to see how they are related. So we're going to sketch a proof of Fermat's theorem by assuming a lot of big theorems. The first thing to note is that we can prove Fermat's theorem if we can prove it for exponent P, a prime, well, a prime different from 2, and or for exponent n equals 4. The cases n equals 3 and 4 were established by Euler and Fermat. So we can start with a prime P greater or equal than 5. So let's suppose that we have a solution to the equation A, B, and C, and this solution has the property that A times B times C is non-zero, and the GCD of A, B, and C is 1. So here's the crazy idea. German mathematician Gerhard Frey realized that if we take these numbers A, B, and C, and we write down the following equation, y squared equals x times x minus a to the p times x plus b to the p. And now we compute the discriminant of this equation. We get the following. So first we compute the discriminant. This discriminant is this number. And now at this equality here, we use the fact that we are assuming that A, B, and C satisfy the equation. So here's where all the magic is taking place. Suddenly, the discriminant became a pth power. Everything that depends on the solution shows up to a pth power. Okay, so we want to determine the conductor of this Frey curve. I told you that there is an algorithm, so the Tate's algorithm does that. So before we apply Tate's algorithm, we note that from the shape of the equation, we can also assume that A is congruent to -1 modulo 4 and that B is even. And by using these two further assumptions while applying Tate's algorithm, we conclude that this Frey curve conductor is going to be 2 times the product of all the odd primes L that divide A times B times C. So in particular, there's no prime to the square in the conductor, so this elliptic curve is semi-stable. So if it's semi-stable, Weyl's theorem proves that it is modular, and because of the corollary, we also know that the mod P-Galois representation is modular for level equal to the conductor of the curve. So we mentioned that, well, the modularity of the mod P-Galois representation can be sometimes achieved by more than one form. So we wonder what's the smallest level that can give us the modularity of this, of the mod P-Galois representation attached to the elliptic curve. So for that purpose, we need the following definition. We'll define the quantity n rho bar E of P to be this quotient, so the conductor divided by MP, where MP is equal to the product of all the primes that divide the conductor exactly once, and P divides the valuation at that same prime of the discriminant. This means that this prime in the prime factorization of the discriminant, its exponent must be a power of p. Must be divisible by p. So if we look, something is not responding. Okay, it's back working. If you look into the expression for delta and the conductor, you can see now that every prime that divides the conductor divides it exactly once. So everything will satisfy this first condition here. And which primes will satisfy also the second condition? Everything except 2. So this number this number MP in this case is going to be this product here, everything except 2. This means that this first n row bar, this number is going to be 2. Okay. I already told you that the mod P-Galois representation is modular of level equal to the conductor. If we apply this big theorem of Mazur, we can also conclude that this mod P-Galois representation is irreducible. And now there is a level lowering theorem due to Ken Rivet, which is too technical to show. But what basically the conclusion is that under these two hypotheses, and with some extra technical thing, maybe then we can actually have modularity of the mod P-Galois representation for the level equal to this quantity, which we have just computed right now, and it's 2. So we have modularity of the mod P-Galois representation at level 2 and weight 2. This is, in some sense, a miracle, because everything that depended on the solution disappeared now. So this number here, the conductor, is a non-concrete because it depends on A, B, and C, but now this smaller level, it's 2. It's a concrete number. So we can compute this space of modular forms. And we do it, and we don't see anything. So this means that using a solution from the equation, we have produced a modular form which belongs to this space, but there's nothing in this space. So we conclude the argument with a contradiction. So this basically sketches the proof of Fermat's theorem, assuming, of course, a lot of machinery. So the natural question is, can we change the field from Q to something else? And the first type of fields that one is led to consider are called real quadratic fields, and they look more or less like this. So we have Q square root of 2. So we just plug in square root of 2 into the rationals, we get numbers of this shape. We have Q square root of 5, or more generally, Q square root of D, where D is some positive square-free number. And we use these fields because over these fields, we have something called Hilbert modular forms, and they will basically replace the classical modular forms. Okay, so every time that I mention an Hilbert modular form, you can just assume that I'm talking about classical modular forms because properties are very similar. Okay, so this is what we are trying to answer. Can this strategy be applied over other fields? And the answer is yes. And the first work on this direction is due to Jarvis and Mikin, and they have proved that over Q square root of 2, the Fermat-Last theorem also holds. And for the proof, they use the theorem of Jarvis-Manohar-Mayun, saying that semi-stable elliptic curves over Q square root of 2 are modular. And now the argument goes basically exactly as over Q. We, again, assume there is a solution. We need P to be at least 17 in this case. We write down the same curve. The discriminant, because the curve has the same shape, is going to have the same properties. Again, we do some extra simplifications. Under these simplifications, we apply Tate's algorithm. It's again a number which is square free, so the curve is semi-stable. This is exactly as before. So the curve is semi-stable. The next thing we know is that the theorem of Jarvis-Manno-Harmayoun says that the curve is modular. So the mod P-Galois representation is also modular. This is exactly as before. And now here's the first difference. We need to prove that the mod P-Galois representation is irreducible. And there is no theorem like Mazur theorem that works for every elliptic curve. But one can get, for more specific curves, one can find some criteria that helps us to get the same conclusion. That's why we need P to be at least 17 in this case. So there is a criterion due to Alan Krauss that basically gives us this conclusion also. So then we have all the ingredients to apply level lowering theorems again, and we do that. And we conclude that the mod P-Galois representation must be modular of weight. In this case, it's just 2 because the field is quadratic, and level square root of 2. Again, we compute this space, and there's nothing in there. So we get another contradiction. And for smaller exponents, the result follows by other kind of method. So this finishes the proof over Q square root of 2 is essentially the same proof as over Q. Okay, so one, of course, this works once. Let's see, is it going to work again? So can we change to other fields like Q square root of 3 or Q square root of 5 and see if this still runs? So, and what we realize that it does work, but there is some work to be done. So what do I mean when I say, does this work over another field? So what I mean is, can we perform the following 5 steps? So step 1, it works because we can define the Frey curve exactly by the same equation. We now take a solution, some solution over a square root of d, Q squared of d. We define with the same equation the Frey curve. Step 1 is fine. Step 2, well, we need to know that the Frey curve is modular. Over Q, we have a theorem of Wiles. Over Q squared of 2, we had this Jarvis-Manno-Harmayoun theorem. And now over a general real quadratic field, in joint work with Li Hang and Sik-Sek, we have shown that all elliptic curves over real quadratic fields are modular. In particular, the Frey curve, if it exists, must be a modular elliptic curve. It follows from this theorem. Step 3, we need to prove irreducibility of the mod P-Galois representation. So this is supposed to be orange because we can do it, but it somehow requires a little bit of work, not too much. But you remember in the previous proof, P needed to be at least 17 for this to work. And sometimes we have to grow this P much more than 17. But usually we can get around it. Step 4, level lowering. This is well established nowadays. So the work of Jarvis, Fujiwara, and Rajai basically says you can apply level lowering all the time. So if certain conditions are satisfied, level lowering is available. So we don't have to worry about this because those conditions, we can check them easily. And finally, step 5, the contradiction. So in the 2 examples we have seen before, this contradiction was just say, well, we have a modular form. There's nothing in the space. We have a contradiction. But what if there is something there? So that's where the main challenge nowadays lies when I'm trying to apply this method to the same equation over other fields or to other equations. Is that except for these 2 examples I've shown you, everything else will find modular forms in this well, everything else that I've seen will find modular forms in this final part. So we don't get the contradiction for free. We need to do more work to get that contradiction. Okay, so let's see what happens over q square root of 3. So if we try to apply this recipe of q square root of 3, sorry, instead of getting a contradiction after steps 1 to 4, we get the mod p congruence from our Frey curve E and some modular form f of this level. But we can also see that this modular form f is actually, due to modularity, going to correspond to this elliptic curve. So this is a very concrete elliptic curve. This is the obstruction to solve the Fermat-Lars theorem over this field. So we need to show somehow that we can still rule out the congruence with this elliptic curve. This is what we do is a bit more technical, but the idea is that we have to analyze what's the behavior of our Frey curve and of this obstruction at certain primes. So this curve has what's called potentially good reduction at this prime. It doesn't matter if you don't know what this means, but what matters is that we conclude from this fact that there is a subgroup of the absolute Galois group, which we call the inertia group at this prime, such that the image of the Galois representation at that subgroup must be of order 2, 3, 4, 6, 8, or 24. On the other end, we look into the other curve, and it has potentially multiplicative reduction. And it satisfies some extra technical condition. But this implies that the image of exactly the same group must be of order divisible by p. Well, these two things can only go together if p is 2 or 3. So we get a contradiction if p is at least 5. So despite of this obstruction, which doesn't allow for an immediate contradiction, we can still pass by this obstruction by looking more carefully at what's going on at certain subgroups. So this rules out the obstruction and concludes the proof of Fermat-Lars theorem over this field. Okay, so another example. So let's move to q square root of 17. Again, after applying steps 1 to 4 over this field, we get a congruence with something which has level 2 and correspond to this elliptic curve. This is again very explicit, so we can check for many behaviors of these curves. And how do we get the contradiction in this case? Turns out that there is a somehow technical criteria due to Halberstadt and Krauss that basically saying that we can only have this congruence if certain valuations of the discriminants of these two curves, so the Frey curve and the discriminant of the obstruction, satisfy the fact that this quotient is a square modulo p, but we can compute this quotient, and it's 8 modulo p. And 8 is only a square modulo p when p is congruent to 1 or 7 modulo 8. Okay, so I can't show you this criteria now, but the idea is that there is something that we can still apply. And okay, so we conclude that when p is not congruent to 1 or 7 modulo 8, then we can also rule out this case. So this is not all the p's. You see, in the previous argument worked for every p at least 5. This argument works for half of the primes. And now, what happens over q square root of 5? Again, there is an obstruction which is given by this curve. Here w is a number in q square root of 5 that satisfies this polynomial. How can we discard this one? Can we rule this out? Well, I don't know. I don't know how to do this. none of the known tricks that work. I don't have a new trick that works, so we don't know how to do it. And one could wonder if, well, does this mean that there is a solution? Probably not, because Alan Krauss has shown that for all prime exponent p at least 10 to the 7, there are no solutions. So maybe there is a solution which is huge, the exponent, or we just need some new trick to cover this. And we could keep going, change this field for another field, and see what comes out. And we have done that for a few more fields, and we have proved the following theorem. So if D is a square-free integer between 3 and 23, different from 5 or 17, or D is 79, then every solution to Fermat-Last theorem over the field Q square root of D for exponents at least 5 must satisfy A times B times C equals 0. And as I've shown you, over the field Q square root of 17, the same holds if we assume that further that P is congruent to 3 or 5 modulo 8. One could extend the list in this theorem by just letting the computer run to give us modular forms and try to discard more and more. But it gets mostly, soon after this D values for D, the computation of the required space of modular forms start to become very difficult. And at some point, we have to decide to stop. So we stopped it here. But one still wonders, what about the general field? Because here we use specific fields, we compute specific spaces of modular forms. Can we do this over a general field? And the theorem we have shown in that direction is this. For a set of real quadratic fields of density 5, 6, then there exists a computable constant B of D, so it depends only on the field, such that all solutions to the Fermat equation over this field for exponents bigger than this constant must satisfy A times B times C equals 0. So this means that Fermat-Last theorem holds over the field if the exponent is large enough. In particular, this theorem holds when D is congruent to 3 mod 8. We have a few more explicit congruence conditions for other families of fields, but this amount also includes fields which are not explicitly given. And the question is, why do we need to allow this constant to grow? So, well, basically, we need to allow this constant to grow to guarantee irreducibility of the mod P-Galois representation. We need it to grow also in the contradiction step, because we can't see the form, so we have to assume that P is very big for many of the arguments to work in general. So these are mostly the two reasons. And the main idea that for the proof is that we can attach, somehow classify this. Most of the obstructions we find are of this type. So many times it's this type, so it works. When it works for all P. And we can somehow describe these obstructions by S-unit solutions to what's called S-unit equations. And then we study those solutions of that S-unit equations over these fields in general. And these fields in general. And we get the conclusion that for 5, 6 of those fields, the solutions are somehow well behaved. So the obstruction is not really an obstruction, and we can conclude what we want. Okay, so this is everything. Thank you. Yes. So if you just take this original equation and change the exponents, let's say if you change for 2, 3, you make some. You can also make some of them concrete and let some exponent vary, like 2, 3p, for example. That's a case where we still have an elliptic curve to try to apply this method. But if you go for example 3, 5p, there is not an elliptic curve. We don't know any that will work. But indeed, there are a billion varieties that might be used to do this. But then you don't have anything. You don't have in general modularity. We don't have many of the other tools are missing. It's some of the things I'm starting to work more recently is trying to make some example work with a billion varieties, but most of the machinery is not in place yet to succeed. But yes, the answer is yes, and it's actually true in full generality. If you replace P by Q, and then the second exponent by R, and then by another exponent L, Henri Darmon has programs in some sense that gives you a billion varieties to those cases. But we don't know much about those varieties, so it's not yet possible to make this work using them. But someday it should work. You mean all curves over all fields? Well, if the field is totally real, it's also part of what we have done. We have shown that if you fix a totally real field, number field, then there are only finitely many curves defined over that field which are not modular. There's no control over these exceptions at all, but we know that for a fixed field there are only finitely many if the field is totally real. And that's the closest thing that I know. But controlling these exceptions seems to be extremely difficult. Actually, if the problem is that, so with modularity, we prove that we get we go from an elliptic curve to a modular form, but we also need to go from a modular form to an elliptic curve, and this is called Deichler-Shimura correspondence, and this is not known all the time. So the last 6 that is missing is also true if we assume that Deichler-Shimura holds all the time. So it's a conditional result. So one could replace this by 1 if we assume an extra conjecture. That should be true, but it's not known.
Bueno, buenos días a los grupos. Bueno, es para mí un placer presentar a la siguiente conferenciante, Rosa Donat. Rosa Donat es catedrática de Matemática Aplicada en la Universidad de Valencia. Es una brillante investigadora que hizo su tesis doctoral en UCLA. Es una de las pioneras de los exiliados que se tienen que ir, pero no fue por exilio ni por falta de trabajo aquí, sino por cuestiones científicas. Y me ha tocado a mí presentarla porque tenemos algunas cosas en común. Rosa es ahora la presidenta de la Sociedad Española de Matemática Aplicada, cosa que yo también fui hace algunos años, y además tiene otra cosa en común, menos agradable quizá, bueno, más costosa, y es que es la presidenta del comité organizador local de un congreso que va a celebrarse en el año 2019. Es un congreso mundial de matemática aplicada. Es como este, pero multiplicado por 7 o 8. Esperemos que por más. Cuanto más se multiplique, mejor. Mejor para nosotros, peor para ella, pero bueno. Así que, muy bien, muchas gracias por venir, Rosa.
No, no le había dado, mentira. Muy bien. A ver, ¿dónde está el mando este? Bueno, lo que os voy a contar hoy es, I should switch to English, okay. I'm going to talk about some recent work that I've done together with my collaborators, Pep Mulet and Paco Guerrero Cortina in Valencia, about a model in chromatography. Analysis and numerical simulations. I'll tell you about it. Okay. So here's the outline of the talk. I'll tell you a little bit what we know about chromatography, which is not very much because we started maybe, I don't know, a year ago. About the model that we consider, how we handle that model, the structure of the model equations, what kind of numerical schemes have been used and should be used for this model. Our choice, and I'll tell you why, this implicit, explicit, unrequeta schemes. And I'll support the use of these schemes with some numerical experiments. And the conclusions will tell you what we think about why these models are useful and should be used by chemical engineers in chromatography. So chromatography is a technique for the separation of complex mixtures. It seems that the name comes back to the early 1900s because the name was used when dyes or plant pigments were extracted. And the true version of chromatographic processes as we know them today, the theory was stated solidly in the 40s and the 50s. And since then, the experimental procedure has improved quite a bit, and it's used nowadays, especially when high purity of the product is demanded, and you can't do it by, say, distillation or similar procedures. And it's very important in pharmaceutical, biomedical, environmental, chemical, etc., such industries. Okay. What we're dealing with here is called adsorption chromatography. Okay. This adsorption is a surface phenomenon. So interaction takes place only on the surface of a substance, which is the adsorbent. More concretely, the experiments and the theory that I'm going to talk about, it concerns liquid and solid chromatography. So you have a liquid, which is called the mobile phase, and it contains a mixture of species that you want to separate. And this mobile phase flows through a packed bed of adsorbent material. Okay. And this material has different affinities the different components in the mixture have different affinities towards this absorbent. And that's what causes the separation. Okay? So the setup is the following. So you have a column containing the adsorbent, which is called the stationary phase, okay, as a porous medium. And then you pass a continuous flow of liquid, a mobile phase with a constant velocity, okay? And then this mobile phase, the solvent, must dissolve the components, but it should allow competition with respect to the absorption power of the stationary phase. Then the components of the mixture interact with these porous mediums as they move, and then the competition between their different affinities is what causes the separation, okay? So for sufficiently long columns and under appropriate conditions, it is possible to collect pure fractions at the outlet of the column, okay? So from a mathematical point of view, what models do they have? So essentially are nonlinear convection dominated PDEs. These are the models that they have. And if you're expected to have pure fractions, then essentially you have nonlinear behavior, you have shock layers, and you have to have numerical simulations to predict expected behavior because analytical solutions are not known. Okay? So the equilibrium dispersive model is an ideal model that nevertheless seems to fit quite well the numerical, the physical experiments. So what are the simplifying assumptions? So you assume a permanent equilibrium between the stationary and the mobile phases. And this permanent equilibrium can be expressed by something which is called an adsorption isotherm. This absorption isotherm expresses the concentrations of the components in the stationary phase in terms of the concentrations of the fluid phase. This is the equilibrium hypothesis, okay? Then you assume that you have the column and you can neglect anything that happens in the radial direction. So it's a 1D process, very nice. And you assume that the mobile phase is not compressible and that the solvent does not interact with the stationary phase. Nothing happens with the solvent. And then the behavior of the system is controlled by convection, okay, and the relation between the fluid in the mobile and the adsorbed phases by the adsorption isotherm, okay. Here I collected a sentence from some of the people. This is a book, Fundamentals of Preparative Chromatography. Guillaume and collaborators are some of the people that have worked a lot on the mathematical side also, even though they're chemical engineers, okay? And here's what they say about the equilibrium dispersive model. So it's the simplest model that takes actual dispersion. They call it dispersion, we would call it diffusion. You'll see it in a minute. Mass transfer kinetics into account. We will not take mass transfer kinetics into account in this talk, okay? Now, the model permits, with a good approximation, the accurate prediction of the importance of cell sharpening and dispersive phenomena due to the nonlinear interaction between the concentration in both phases, okay? Now, this in turn results in correct prediction of the band profiles and the achievement of an excellent agreement with experimental data. This is what drives simulation. You want to have a model that can predict expected behavior. And you want to be able to model, to obtain the simulations in a very robust and accurate way, okay? So what is this model, okay? So if you only take into consideration now in this talk that axial dispersion, in fact, diffusion, okay? So as you go down, things tend to, broaden, okay? So this is the only mechanism that causes band broadening in the mixture, and you neglect any additional factor that could influence the behavior with respect to absorption, and you consider the general mass balance equation. Then you relate. Oops, okay, here. You relate the variation of the concentration on the mobile phase and the solid phase. Okay. Here is the velocity of the mobile phase, and you get a relation like this, okay? This is a sort of a geometric factor that relates the volume of the stationary phase with respect to the mobile phase, okay? And this dispersion coefficient is what causes band broadening, okay? I'm not gonna get into details of what this thing is, but it's proportional to the length of the column and the velocity of the mobile phase. Okay, you make this constant. So you make the carrier flow at the same velocity always, okay? Now, the key thing here is the absorption isotherm, okay? So if you have a homogeneous porous medium, you have a uniform absorption behavior in time and axial direction, and then you can express this relation, this absorption isotherm, as purely a function of, so this states that the concentrations in the stationary phase are a function of the concentrations in the mobile phase alone, okay? And this function, its natural domain of definition is it's the Rn. At least one concentration is non-zero, okay? So what is the structure of the system? So obviously, if you set dA equal to 0, you have a system of nonlinear first order PDEs. And if you have dA larger than 0, then you have a parabolic. If this guy is small, then you have a convection-dominated system of PDEs. This is the case of interest, okay? Now, what is the mathematical structure? So it depends on this Q. This is what happens. Depending on what Q is, the behavior could be different, okay? So over here, in this talk, we're going to consider adsorption isotherms of Langmuir type, which correspond to the convex case, say, the easiest case. So this states that the concentration of the ith component on the stationary phase is proportional to the concentration on the mobile phase. This AI coefficient here states the affinity, larger affinity, then more stuff stays in the stationary phase. And then there's this nonlinear behavior here, which is the one that causes the sharpening, okay? The nonlinear behavior in the solution. So if BI is equal to 0, then you have a linear model. Linear models are not appropriate in many situations. And no sharpening mechanisms appear in that case. So how are the solutions? So solutions, you expect them, you want them to display. That's what you state this process. May display very sharp fronts. Analytical solutions could only be obtained in very simple situations, usually not in a real case. Okay. Therefore, if you want to predict something, how long has to be the column so that I can extract pure ice at the end of the column, you have to resort to numerical simulations. And you need efficient numerical techniques because solutions with sharp fronts are hard to compute, okay? So what have chemical engineers used? Just about anything, okay? Finite difference and finite elements are the things that are off the shelf. They have used them. But they're not appropriate for discontinuous light behavior. You have to be careful with that. They have turned to finite volume schemes as natural candidates. They originally designed for conservation laws. This is where I come from, so we know about this. They may resolve accurately discontinuous light behavior, provided that a conservative scheme is used. This is important, okay? So it is important to develop tools that are able to perform accurate numerical simulations using these models. And what we saw is that they're not that accurate, and let me tell you about that, okay? Here's the motivation of our work. Here's how our work started. This is a paper in computers in chemical engineering in 2011. So they start with the model that I just told you about, where it came from, with adsorption isotherms of Langmuir type. And it is implicitly understood that you can go between what is in here, which is derivative with respect to t of this quantity, plus derivative with respect to z, which is the length of the column, I mean the actual variable. This thing here you can go back and forth between this W and the C, implicitly assumed. It's like the one-to-one correspondence, but you don't have it. They didn't have it, okay? But assume that you had it. So they say, well, I have a conservative formulation, a finite volume scheme. This is nice, okay? So over here is where you can use all the technology for shock capturing. And this is what they propose to do, okay? Over here, I want to invest in high tech to get very well non-oscillatory shock profiles, okay? But you cannot update the W because you only have the C. And if you update the W, you cannot go back to the C because you don't know this relation over here. So you cannot update directly the W, and they know that, okay? So they go back to the old days. So if you look at the original papers by Guillaume Sean and all these guys, they always turn to this form, this linearized version of this equation here, where you introduce the derivative of the absorption isotherm with respect to the concentrations. And you solve this, okay? But you're not conservative. And what does this mean? Your shocks are not in the right place. That's what it means, okay? And let me show you, in a bit I'll show you what it means. Shocks are not in the right place, okay? So what are our main results in this context, okay? So the main result is that this thing here does have a globally well-defined inverse. You cannot give it explicitly. So you don't have a formula in general. For n equal to 1, you can do it, but in general, you don't have a formula, explicit formula. But you can compute it. And if you can compute it, then you can, the machinery can work, okay? The nice thing about all these things that I told you here is that you can get, as a byproduct, some of the mathematical structure almost for free. You can get strict hyperbolicity, you can get well-posedness of the model, and all this means that you can use state-of-the-art, high-resolution, fully conservative shock capturing schemes. You can apply them to the equilibrium dispersive model, and you can make robust simulation tools that can be obtained by nowadays standard techniques, okay? And our choice is this MX runner schemes. Okay, so let me tell you a little bit about how we attack this invertibility of the function that relates, that allows you to go to the conservative formulation. All this is a consequence of the analysis of the Jacobian matrix, okay? And this analysis uses some tools that we have been used over the years. We have used over the years, and we thought that we could apply them here too, and this is the case, okay? So you have this function here. There's the function that appears in the slide before, that is the conserved variable, okay? And here you have the concentration, and here you have a linear part, and here's the nonlinearity, okay? Specific form of nonlinearity that allows you to do a lot of things, okay? So we can prove that for any vector of concentrations, so that all the concentrations are strictly positive, the Jacobian matrix is diagonalizable with real strictly positive eigenvalues, okay? So here's some notation that allows me to write less in the following transparency. So the denominator here, I call it P of C. Okay, note that this thing here, whenever I have just one component which has a positive concentration, this thing here is larger than 1. So the set of interest is contained in the open domain of this function here, okay? So as a consequence of this theorem, which holds for whenever the concentrations, all the concentrations are strictly positive, as a consequence, I get that the Jacobian is non-singular in the natural domain of the function. And the inverse function theorem guarantees the existence of a local inverse. But in fact, the inverse is global, okay? And this is the important thing here. Okay, so what is the proof? The proof is so simple that I can attempt to tell you about the proof here, okay? It's an argument that I think it deserves to be better known by our community, the community of people that use numerical techniques to handle complex PDEs or ODEs. and that the technique is known by the linear algebra people, but what we learned the first time we used it is that it stayed there. It didn't permeate outside. So some of the things that you can do with this theory are very hard to do if you don't use it. Okay. So let me tell you about this thing a little bit. So here's the function. Okay. So you can compute the Jacobian. That's very simple. Okay. I don't want you to follow this thing. But I want you to realize that this Jacobian can be written as a rank 1 perturbation of a diagonal matrix. This is the key point here, okay? Now, the eigenstructure of these matrices can be easily obtained. And this is what I tell you that, I told you that linear algebra people know this, and some of our people didn't know it and you know, had to work a lot to get the structure without using this secular equation approach, okay? We learned it from Joel Anderson in a paper in 1996. We used it in a series of papers with Pep Mulet and various collaborators, and always simplified a lot the things that you had to do to get the eigenstructure, okay? So how do you get this eigenstructure? So here's the diagonal plus the rank 1 perturbation, okay? And here's the eigen vector, x. And so you pass this over the other side and assume that your eigenvalue is not one of the diagonal values. So you can invert this matrix here, okay? And from here, you invert and pass to this relation, multiply by b again. And if this thing here is non-zero, then what should be 0 for that lambda should be this expression over here, okay? This is a scalar relation, okay? This is a rational function that you can write in terms of your d and your z, which you know, okay? This is a rational function. So if something is a root of this function, maybe you should look at this function here, okay? For this function, you could draw it, okay? So you can compute various things about this function. For example, that s of 1 is positive between 0 and 1. You can compute the limits when lambda tends to plus or minus infinity. And if you have the pole, that is, if the component Ci is positive, then you know the behavior at the pole, okay? So here's the picture of a function, of one such function. Now you look at that function and you see that if all the poles are there, then this function has at least n roots. You just look at it and you can compute them because you know where they are. You can compute them. There's no problem computing any of them, okay? It is easy to see that these are the only roots because you can multiply by the denominators, get a polynomial, which is of degree n, that has the same roots as this function here. So it can only have n. So you have all the roots of this rational function, okay? Now, if you have all the roots, you can easily show that if all the poles are there, that is, if all the Ci's are positive, then you have all the eigenstructure. That's all there is to it, okay? So if it has, if all the concentrations are positive, then this function here has this many roots interlacing the poles, and here are the eigenvalues. Then this matrix is diagonalizable, okay? Now, as I told you before, if some of the components are 0, but not all, we can deduce that the Jacobian is invertible. And the inverse function then guarantees the existence of a local inverse, which in fact is global, okay? So what is this inverse? So here's the inverse, okay? Here's the function, okay? What is the inverse function? How do you go back from C to W? So here's the inverse. It looks very much alike. Here's a rho 0 of W. What is this? So this is a root, the only positive root of a given rational function that you can easily construct just by your data, which is the W that you want to find out the n-time image and the data of the problem, okay? And why is this? So it's more or less the same argument. It's a very nice argument, okay? So assume that you have a set of concentrations, a vector of concentrations, and you take the image by W, okay? So here's the image. And if you solve for Ci, here's Ci, except that Ci is also over here, down there, okay? So here's the implicit relation, okay? Now, if you write what P of C is, which is this thing here, and substitute the Cj by this formula here, you easily arrive to the fact that P of C is a root of, this is 1, y, so it's a root of this function, okay? So this P of C, which you need to invert, is in fact, you can find it as a root of a rational function. Now, how many roots does this function has? Can you find them, okay? So you draw it again, okay? So this rational function, shaped like this, you can again find its limits and see the behavior, you plot it, okay? And if at least there is one Wi larger than 0, if at least there is one pole, then for whatever it is, okay, there's only one positive root, only one, okay? And if you have it, I mean, you know that easy bounds, okay? You can, at 0, you know that this function, the value is 1, okay? So it's here. And then at 1 plus B transpose W, then you can compute that the value is below 0. So the root is right here, and you can compute it by any means, your favorite solver, okay? Non-linear solver. So you can actually compute this thing. You have this thing that you need. You can compute it easily, okay? Easily. So here's the W, here's the C. That's all there is to it. And you can go back and forth between the two of them, okay? You can easily show that one is the inverse of the other. It's very simple. In fact, the truth is that the P of C is this root of this function. If you start with a C, then you find that P of C is the root of W. Define that way. If you start with a W, then you find that P of C is the root. Okay, so these two things are exactly the same thing. So it's like substituting P of C by the root that you have found. Okay. So what do we have? So we have that we have in fact that this function that we have defined is C1 because the inverse is unique. Very easy. Okay. See, if you have a vector which has may have some component zeros, but at least has one component non-zero, then the same component in C is going to be a non-zero. And if this thing here is invertible, the inverse function theorem relates the two Jacobians, okay? So if all of them are positive, then the eigenvalues of these guys, this C prime, we know them because they are the inverse of the eigenvalues of the W. So I mean, here's everything. You can compute them also. You can compute everything, in fact, okay? You not only you know that the system is hyperbolic, et cetera, but you can also compute everything because they are the roots of something which is easy, very easy, okay? So what is the main consequence? It is possible to work with the conservative formulation. You don't really have to go to any linearization. There's no need, absolutely no need, okay? Very good. So let's go back to the conservative formulation, okay? So we have the model, okay? The Q is given by a Langmuir type, okay? We have the W, we have the C, everything is ready in our hands to compute, okay? Here's the conservative formulation, okay? Let's look at it again, okay? If you put dA equal to 0, this is a system of conservation laws, which is a strictly hyperbolic for when all the components are positive, in the region where all the components are positive. If dA is positive, we can also show that it's a well-posed convection diffusion system, okay? And I already put, I repeat the information that I gave before, okay? Here is the convective derivative, which is the Jacobian matrix. So the F is U times C, okay? C, I know that is a well-defined C1 function. The Jacobian matrix is U C prime, and here are its eigenvalues, okay? So all propagation speeds are positive. Everything is going down the column, as it should be. And they're all smaller than the velocity of the carrier. That's as it should be, okay? What about the parabolic system? Okay, so here's the diffusion matrix, the AC prime. So here are the eigenvalues of the diffusion matrix here, okay? And they're all bounded below by something that I know what it is, okay? So from the practical point of view, it means that you can compute, okay? You can set up robust schemes for that. Okay, so let's recap here. So we know that we should confront, or we should be prepared to deal with discontinuous fronts, sharp profiles, in fact, when the A is positive. We know that the solutions were hard to compute in the old days, but they're not hard to compute anymore if you use the right tools, okay? You need to use high-resolution shock capturing schemes. You need to use a conservative scheme. You need to use conservative formulations, okay? If you want to respect all the properties that the physical system has just by having this form, okay? And if you do all that, you can expect non-oscillatory solutions, you can expect robust behavior, okay? So what is the computational setting for the schemes? So you have the column over here, okay? You decide how many mesh points you want to put. You define your mesh, here's for convenience. This has to do with the boundary conditions that I've said nothing about them, but it's okay. And here's the space, delta Z, okay. So how do you construct a high-resolution shock capturing scheme? So first, you go to a method of line discretization. You separate the spatial and temporal accuracy. You don't have to do that, but this is simple, okay? And here's the part that's going to give you the non-oscillatory behavior of your scheme, okay? This is the numerical flux at the cell boundary, and you can do this by highly sophisticated technique. We not schemes or maybe flux limiting techniques. This is what these chemical engineers use, whatever your favorite, that works, okay? You can do, and here's where the power comes. This is very complicated, but nowadays is a standard. If you put Win05, you can download a MATLAB program, and you don't have to know how it works, but you have to know that the way it works, okay? But not just like when you get something like this, you have to just to know what buttons to push, but you don't have to know how it works inside, okay? Oops, here, okay. Then for time accuracy, use an appropriate ODE solver, okay? All right, so let me just show you a first order scheme, just to highlight some of the things that I want to tell you later, okay? So suppose that I use the simplest possible thing, which is first order upwind numerical flux. Upwind means that the flux should look in the direction of speed of the propagation speeds in the system. They're all positive, okay? So if the propagation speeds are positive, you should look to the left to get information, okay? So the natural upwind numerical flux is here, is this one. You look to the left at the J+1/2 interface. And you just use a simple center difference for the diffusive fluxes, and you get a first order scheme, which is something that you probably show your students in one of the numerical analysis classes if you teach them, okay? So this is conservative, this part here, fully discrete, a scheme first order in space and time. This is what the chemical engineers could not use, okay? Why not? Because you cannot update W, right? If you update W the first time, then you cannot get C the next time, okay? Because they didn't know how to do it, okay? They didn't have that relation. We can do it because once we update W, we can the next time step we can get C. We can do it, no problem, okay? For practical purposes, finding C only requires to find the only positive root of a well-defined rational function. I know where this root is. I can compute it like that, okay? All right, so here's what they proposed, okay? Can't do that, cannot do it, so I linearize. And then I In fact, they did this on MATLAB, okay? Here's where they put the power of the high-resolution shock capturing scheme, right here, in the computation of the numerical fluxes of the convective derivative. They didn't get any oscillations. I'll show you results right now, okay? But their scheme is not conservative. And this is what it means, okay? We take one example, one component. It's called single illusion. In their terminology, it means that the component dissolves somehow in the mobile phase. And in one component, you don't even have to resort to computing the roots of a rational function, or if you do, this is what you get. Whether you go one way or the other, you get to the same side, okay? And in red, you have the conservative formulation, and in blue, you have the non-conservative formulation, and you see that the non-conservative formulation lags behind. The shocks are not correctly situated. And you may say, well, yeah, right. And why is the conservative formulation the good one and not the other one? So here's a table to convince you, okay? So we're in the conservation law case, so dA is equal to 0. There's no diffusion. Everything that should be conserved must be conserved, okay? So this is what should be conserved at the PDE level, the total mass of what says the PDE that should be conserved. So you compute this discrete version of that, okay? And you look at the non-conservative formulation, you have a first-order scheme or a second-order scheme. The non-conservative formulation, the one of the chemicals engineers, versus the same thing but conservative, that is computing, updating the W's. And you see here that what should be conserved is conserved while you're losing mass here. First order, second order, you always lose mass. So those results are not correct. Whether that matters or not, is maybe you can live with that, but it's not correct. It really is not correct, okay? So we're fine. We use these schemes, or maybe not. Maybe we can do it better, okay? So I claim that we can do it better. And what does it mean? Well, it means that using an explicit scheme I'm not being as efficient as I could. And why is not that? Okay, well, because of this. If dA is equal to 0, you have a conservation law. This is a standard theory, and you know that in order to ensure numerical stability, you have a CFL condition. And the CFL condition involves the maximum propagation speed of the convective derivative. And it reads like this, okay? So you should have all propagation speeds that may happen controlled, okay? So for our system, since we know that all these guys are less than 1, because we have computed, we have shown that, then this is the relation that should be respected for numerical stability, okay? Now, if you have a convective term, then this term here appears. So you have increment of t over increment of z squared, okay? So by the same bound on the propagation speeds, you have that with respect to what you had when you have dA equal to 0, you have a reduction of the time step, necessary reduction of the time step. And you said, I don't care. Well, this is what you get if you don't care, okay? So here's dA small value, okay? And a value of increment of t over increment of z equal to 0.84, and you get numerical instability. You don't want to have that for various reasons. One, it's ugly, and second, it can trigger all sorts of ugly things for you, and bring you to a place where you don't want to go, okay? So you really have to respect the numerical stability, and there's no reason why you shouldn't do it. If you turn to implicit, explicit Runge-Kutta schemes, why are these guys good? Because they only do an implicit discretization of the parabolic term, which is linear in this case, okay? And they do an explicit discretization of the convective derivative, where you have invested a lot of work because these guys are tough, okay? The numerical fluxes, okay? So, is this going to cost me a lot? Because if I save on the time step, but then I have to pay a lot of price because this is very hard to do, maybe I shouldn't do it, okay? So here's how you set up Nimex Runge-Kara scheme. Okay, it's more or less what I told you before, just to set the terminology. Okay, so here's the convection diffusion equation. Here's the convective fluxes. Here's the diffusive fluxes, and the semi-discrete formulation is separated in the convective part, which is nonlinear, very hard. You don't want to touch that, and the diffusive part, which is in this case linear and most of the time easier to treat. Okay. This thing here, you're going to do it with a we know numerical flux, blah, blah, blah. And over here, you need a diffusive numerical flux. You adjust it to your accuracy, the required accuracy, okay? So just to show you what are the numerical difficulties of this type of schemes when we go to the model, to the equilibrium dispersive model, I can just show you what happens with a Runge-Kara 2 scheme, okay? So here will be a simple one, okay? So you have a middle step, right, where here's the implicit part, only the diffusion part. You don't touch this thing here. And then at the next step, you just update Wn+1, okay, with the values that you have over here. You only have one step where the thing is actually nonlinear, okay? The first step, we need to solve a nonlinear system of equations. So for second order accuracy, we're just happy using centered difference for diffusive fluxes. That's what we do. And off-the-shelf numerical fluxes of the appropriate order, we know 5. It's a simple one, no? Okay. What is the problem here? Again, this guy is not explicitly given. I cannot put the W's here because the W's are implicitly given through this root, okay? So I cannot do that. So can I get out of this? Sure, okay? Again, because of the form of the isotherms. Here's the form of the isotherm, okay? So if I take this thing here, I rewrite it using this expression, put everything that has n+1/2 to the left side, I realize that I have a nonlinear part and a linear part, okay? This nonlinear part, in fact, is diagonal. So it only appears in the diagonal. So if I look at it, in fact, this nonlinear, this concentration at n+1/2, vector of concentrations, at each one of the mesh points, I can find it by solving a nonlinear system that has a linear part and a nonlinear part, but the nonlinear part is diagonal. Okay, so I can use a Newton's method. I can do the work, okay, and I can see that the computation of the Jacobian, the inversion is just solving a system, okay, solving a system. What type of system do I have to solve? It's a system that is a triagonal system. This is cheap. This is just as good as, an explicit thing. So it's not worse. It's not worse. What happens if I go to n components? It's the same thing. It's exactly the same thing, but it's harder to write. Okay. So what happens at the end of the? Well, you have a matrix of unknowns. Okay. For the components, the I. For the mesh points, the J. But you do the same thing. You arrange things as the ODE people have shown us to do. And you arrive to the same type of system, but now you have, when you go to the Newton's method, you realize that you have to solve block tridiagonal systems with small blocks of the size of the components. Usually could be 2, 3, 4. This is small, okay? This is cheap. You can afford that, okay? So all the technology that we have could be put to use in such a way that you can actually design, okay, later. We can actually design a robust scheme, which is not much more costly than an explicit scheme, but has the advantage that you can take the relation between the time step and the space size. You can take it as high as you would with the hyperbolic case, okay? So here's with a purely hyperbolic case, and this is what you would expect of a single component elution. So you keep the front as a shock layer now, and this actual diffusion effect is showing up over here, okay? So it's all very nice, and we can put it to work in 5, 6, 10 minutes that I have left. We could put it to work in a real situation, okay? So this is a test that we took from the same paper that motivated this work, chemical engineering, and three-component displacement chromatography, which is part of preparative chromatography and is used, this is in experiments. And the setup is the following. You have this column here, okay? And you assume that you have one component which can displace the other components from the stationary phase. So it's like pushing them, okay? It's like pushing them towards the end of the column. So in the end, what you would like to get at the end of the column is pure substances of the ones that you're interested in. This is what you would like to get, okay? And you need to know how long the column is. You need to know if with your data, this is going to separate or not. These are the things that you want to know. So you set up the experiment or you do the simulation. If you do the simulation, your experiment is going to cost less money. So this is where the interest of the simulations come in, right? So, oops, here, okay. You have to have appropriate conditions to form these isotachyc trains, which are, you'll see it in the next transparency. They are, I have it written it somewhere, highly concentrated and separated rectangular zones, okay? Which is what you want to see. This is how you want to see. This is how you're going to separate your components, okay? So here's a first test, okay, where you have two components injected initially, and then the displacer with concentration equal to 1 at the outlet at the top of the chromatography column, okay? And here are some parameters, the same as they had, okay? And here's how the isotachyc train is formed, okay? So here you see the displacer, the two components, the two concentrations, and you see how the displacer is pushing them, and you see how this highly rectangular region, concentrated rectangular regions of pure substance components is being formed. And over here, if you put the outlet here, you know that you're going to get a pure substance in the first, the blue case, and then one in the red case over here, right? Okay, here's a close-up, okay? And here's a second test where this doesn't happen. What was changed? What was changed here was the concentration of the displacer. You have to have enough displacer, otherwise this will not happen, okay? So the displacer is pushing, but the isotachyc train is not being formed, okay? So it is important to have simulation tools. And what I hope to have shown you is that it's not that hard. Really, you have to work mathematically a little bit, but all the theory that you put in there pays back, okay? And you can use a lot of technology that is in there to help, okay? To help simulations, to help real life experiments, okay? And hopefully to reduce the cost of doing all these things. So I've arrived to the conclusions I just read. I sort of said everything along the way. We can use fully conservative numerical schemes for the equilibrium dispersive model with this type of isotherms. Okay, there's no need to linearize. This is possible because we have a one-to-one smooth relation between the physical concentrations and the conserved variables, which involves the physical and the concentrations on the mobile and the stationary phase. This relation cannot be given explicitly, but we don't care because we can compute it, okay? As a byproduct, we get all the eigenstructure of the involved matrices, so you can compute them if needed, okay? And then I show you that we can actually use Imex-Runge-Kutta techniques, which are state-of-the-art, okay? They are very efficient, and they can be done at a reasonable cost if you invest in mathematics, okay? If you invest in the mathematical technology that is behind that, okay? But it's well known anyway, okay? So I would conclude saying that we know Imex-Runge-Kutta schemes do provide robust and reliable simulation tools for preparative chromatography. And we hope to be able to talk to chemical engineers. We have a few close by and convince them that this is a useful thing, a useful simulation tool. Many thanks for your attention. Here are some of the references that we've used for our work. Thank you very much. Allá. Monty.
So when you use this Nichols method in the street, are you sure that the system only have one solution?
I was hoping that. No, I'm not sure. But I only find one, and I found the one because everything works. But you're right. You're right. We haven't invested any time at all in proving that the solution of the nonlinear system is unique. You're absolutely right. It must be, I'd say, from what I see. But no, we haven't done it.
See, the implicit part of the IMEX method is due to the diffusion component of the problem. Have you thought about using Runge-Kutta-Chebyshev methods?
No.
No?
No. Essentially because we don't have any experience on that. So what we've done here is to put together all the tools that we knew how to use, justifying that we could use them. So as I said, I mean, we saw this paper and okay, high resolution shock capturing the scheme, but you're not being conservative. So can you do it? Okay. And we haven't looked into anything else because essentially because these things we can put them together. Okay. So we know how to do everything that is in there. So it's not, I mean, it's not very elementary mathematics, but they're well known at this point. So our point now is to convince these guys that you can do it. If you can do it well done, why would you want to do it incorrectly? This is the
Yes. Any other question? Okay. Thank you very much.